will be shared in it will be shared in my YouTube channel for revisiting later.
Right. Thank you. So we can start. So before we get into what exactly blockchain is, we first have to understand what exactly is a distributed system. So I don't know if someone could really just tell us what exactly is a distributed system. You can type it on the chat, or you can you can type in the chat, or you can just unmute. What is a distributed system? Okay. So a distributed system, basically, you can think of it as multiple computers that basically are interconnected, and they seem to behave like a single computer. So a good example of this will be the internet. When using the internet, you might actually think that all this is coming from a single computer, but in real sense, it feels like it's coming from a single computer, but in real sense, you have millions and billions of devices communicating with each other over the internet to give you the content that you're looking for. Okay, so that basically is a distributed system. And ideally, in a distributed system, we now have the concept called decentralization. And so the idea behind decentralization is that you have all these intercommunicating devices, but they're now, in this particular sense of decentralization, they're behaving in such a way that the things to do with decision making and how they operate, there's no like a single central server that's basically coordinating the operations going on in the system. Okay, and so that's basically what we mean by decentralized system. All right. So, and it's also good to note that decentralization does not necessarily mean that when a system is distributed, doesn't necessarily mean that it is decentralized. Okay. That's basically it. Like all decentralized systems are distributed, but not all distributed systems are decentralized. You can have distributed systems that are very much centralized. A good example, as you can see there, we have Napster and Nutella. So Napster basically is as you can see, P2P file sharing network, but for this, it had a central server that was basically being used for content and peer discovery. And now, since it was a central server, ideally, we now have a situation where it could be basically shut down. You just have shut down the central server. We have the whole network being rendered completely useless. But now we have another example of what when now come to decentralization, you have Nutella. So Nutella basically is designed in such a way that it was basically the first fully decentralized network of its kind. If you shut down like a single peer, it doesn't end up affecting the entire network. The entire network can basically be operated without the need of another peer or one peer being shut down. Another that's basically what we mean by a decentralized system. It's really just a distributed system, but it has its own mechanisms to make sure that it doesn't really rely on any central server to basically operate. And that is basically what the blockchain is. Blockchain is basically it's a decentralized distributed system. Okay, so at its core, it's a peer-to-peer distributed ledger that is cryptographically secure, append-only, immutable, and updatable only via consensus or agreement among peers. So because of this, we now have the blockchain being completely decentralized. Okay. Yeah. So up to the I hope is there any questions till that particular point? Any questions? Okay, so please, if you have any questions, kindly feel free to type on the chat. Then we can proceed now to different parts of the blockchain. So when you come to the blockchain network, like in the first bit, we can look at his network overview of how a blockchain looks like. So, well, you can think of the blockchain as a layer that it runs on top of the internet. So like you have the actual internet, then now we have another layer on top of this internet. So, and basically we now have our nodes running on this particular layer. So what do you mean by cryptography? So, cryptography is ideally the state of, it's an art of concealing information. So if you want to share information between let's say between two parties, and you don't want another person to basically be able to see what you'll be sharing between these two parties, what you'd use now is now this process called cryptography. So we'll be looking more into it tomorrow. So but just to give an example, when we mean by cryptography, when someone's talking about encryption, like let's say the WhatsApp usually says that your texts are fully encrypted. That basically means that no one else apart from you and the other person can see the text that you're sending. And like they cannot intercept a particular communication, the communication between you two. That basically means it's encryption. Like even if you're to get hold of that information, it basically cannot understand what you're looking at. That's basically as a result of cryptography. So we'll be looking at cryptography more in depth tomorrow. Okay, thank you, Pat. Tech quiz. Yeah, as we are saying, the blockchain, you can think of it as another layer that runs on top of the internet. So we have the different bit parts. As you can see, that's like a network overview of how the blockchain basically is. We have the P2P network protocol that the blockchain network will be using. Then within now the blockchain itself, we have we can see we have a component called transactions. We have another one called blocks. We'll be looking at consensus, what we mean by state machine. We'll be looking at blockchain applications. As you can see, there's the smart contracts, and now there's the users and nodes. So again, remember, we'll not be going into depth in how in this particular the designs for each and every single component, but we'll basically be mentioning it. And ideally, I'll be giving you like a base knowledge on what to expect, so that when now tell you not to go look at Ethereum, you'll be able to understand by what basically we mean by a transaction in Ethereum. How does it look like? That's basically what we're looking at today. So I think you can get started. So the first thing blockchain is addresses. Now, when we're trying to communicate within a blockchain network, of course, before you try to do any sort of sending any crypto within the network, we have to know where this crypto is coming from, and also have to know where this crypto is going. And this is basically done using an address. So addresses are unique identifiers that are used in a transaction on the blockchain to denote senders and recipients. So basically, if you were to look at if you look at blockchain network, trying to look at the blocks and everything, the first bit you can see about those particular transactions you see on the blockchain explorers, other addresses. So each blockchain network has its own way of deriving addresses. As you can see from the examples right there, you can see a Bitcoin address is quite different from an Ethereum address. And the same also applies for other basic addresses. So these addresses, as we'll be looking at tomorrow, are derived from a public key, or they are derived from a public key, or they can actually be your public key, depending on the network you're using. And it's also good to note that when using such kind of an address, it doesn't necessarily mean that you're anonymous. A good example is Bitcoin. Bitcoin is, even though the addresses, you cannot basically tell, like, from that address, you cannot tell, let's say, if this was my Bitcoin address, you couldn't tell that this is mine. But there's been research that has been done. Okay, I'll answer that in a few, Sandra. So there's been research has been done on addresses that on, let's say, like on Bitcoin, that basically shown that you can be able to tell who a particular person is from the address itself. So as a result, you might end up having some blockchain networks being referred to as pseudonymous systems, but you can have totally anonymous systems like Monaco, that basically ideally you cannot you can ideally stay anonymous within the transactions. One way to do this is you might end up finding people who are with each particular transaction they end up generating a new address. So yeah, but really that's basically the basis behind the addresses. Like it is really like this, think of it like your ID within the blockchain network. So what's the differences in addresses? So under the hood, each network they don't have similar characteristics per se, but depending on the network itself, the method of deriving that particular address changes a lot. Like you might find the process of deriving an address in Bitcoin is much different from the process of deriving an address in Ethereum. So allow me to get into the specifics of how these particular addresses are generated tomorrow. But just for now, just know that depending on whichever network you add, the addresses are derived in a different way, but all of them are derived from the public key, or they are the public key itself. Okay, great. Then after addresses, we can now for value from one look at you can look at the parts of the address. Yes, look at the parts of we can now look at parts of a transaction. So educate Agbo, all decentralized. Well, okay. So a good example, I think, for that educate, what I can say is, let me give an example of a distributed system. Let's say a good example is even this Cloudflare. Remember, a distributed system could be anything basically. It could be a company, depending on how they basically built it. But ideally, the idea behind the distributed system is to you as a user of that system, you should basically be able to know that there's thousands of services running behind. For it should look like a single thing, like a single system. Okay. But ideally for distributed systems, you might have let's say like you might have like a single server. Basically, let's say that if you're working on, let's say, like a e-learning system, it's coordinating things like course information, etc., etc. But now you see at that point you have single central servers that are ideally handling very crucial information for the whole system. So meaning that if your identity server falls down, that means authentication basically fails. Now, for this decentralized system, it's a different scenario. For this decentralized system, you find that all these basically, you can think of it like all these operations are handled under one system. They can be handled under one node. Okay, entity, the access to information you need to operate in that particular system. Okay, so as a result, you can decentralized systems, actually all of them are designed in a distributed manner. Like when you're using the network, you should basically be able to tell that it's a single. For you, should feel like it's a single computer that's handling everything, but in real sense, it's a really distributed system. But under the hood, it's different how it basically operates. That the node by itself can operate without the need for another node to basically be up. So they need to, and the entire functionality of a particular network will still be gotten from this one node. I hope that's a bit simpler. Yeah. So back to transactions. Now, so the first bit of a transaction is a version number. Another thing to note about the transaction is it cannot the size is, since we because of the how can I put of the network, you can have where you possibly can have billions and billions and trillions of transactions within the network. The sizes for transactions are basically the capped. Okay, the capped. They can't grow to up beyond a certain limit. So you find that each network has its own designed on the limit of the transactions. But overall, under the hood, some of the specifications of how of these particular data structures we have within the network are the same. So you find like the version number. Now, let's say like this is a transaction for Bitcoin. So we see like in this Bitcoin transaction, the version number is kept at 4 bytes. And as you can see, it's the version number is basically just used to specify rules to be used by miners and nodes for transaction processing. Okay. So depending on the version number that's there, you might end up having different rules for that. Then we have an input counter, which basically represents the number of inputs included in the transaction. So we'll be looking at an example of this in the next slide. List of inputs where the size can be variable. But the list of inputs, it can be composed of several fields. As you can see, we have the previous transaction hash, previous transaction output index, etc. Then the first transaction on the block, which is also called the coin-based transaction, is specifies one or more transaction input. So basically, this is again just to put into context. This is really the structure of a transaction of a Bitcoin transaction. Then we have an out counter, basically a positive integer representing the number of outputs. Then the list of outputs is with the variable size is basically all the outputs including the transaction. Then you have a lock time, or in some cases it's called an end lock time. It defines the earliest time where a transaction becomes valid. So it could be either a Unix timestamp or a block number. Okay. So yeah, that's basically it about the structure of a transaction. So again, remember this might change depending on the network you're using. This is information that's good to have as a blockchain engineer. It's not like a must for you to have, but the thing about you having this information basically helps you in designing your networks much more efficiently. Yeah. So and I think just in the case of Bitcoin, the lock time might also be known as end lock time. Basically, as you've seen, basically defines the earliest time that a transaction is valid and can be laid into the network or can be added to the blockchain. So if it is non-zero or below 500 million, in the case of Bitcoin, that basically is taken as a block height, and basically means that the transaction is not valid and it is not relayed or included in the blockchain prior to the specified block height, meaning that and not until the block height for the height of a particular block where the transaction is, if it doesn't reach the specified block height that's specified by the lock time, that particular transaction wouldn't be recorded as valid. Okay. Now, if it is above 500 million, we now start interpreting that particular time, the unlock time as an Unix epoch timestamp. And basically that's now where we basically wait, where the network basically waits till a particular specified time so that the transaction cannot be recorded as valid. So yeah, so remember, this information may change depending on whichever network you're using, but again, this is like sort of like the base knowledge. Like this is where the progenitor of most chains use the knowledge from. So kindly make sure that whatever we do right here, it's also good as an engineer to go and read beyond what we do right here so that you can be able to learn more about these networks and you can be able to now design more efficient dApps. So I think we can now look at an example of a Bitcoin transaction. So this is so as you can see, we have the transaction ID, We have the hash, gonna have the size of the transaction. See the version right there, which you talked about. The version is right there, number one. Then there's lock time, which we from talking about. As you can see, it's above 500 million, meaning that this transaction is only valid after the epoch, the timestamp, basic the epoch, Unix epoch timestamp past this particular specified time right there. So as you can see, we now have the inputs, as you can see here, and you also have the outputs right there. As you can see, we have you can see right here, just have one specified output, a transaction ID for this. Then I think we have something called a script sig here. So in the context of Bitcoin, the script sig, it's basically how do I put it? A script sig, it contains signatures and scripts that basically unlocks allow me to use the money within the transaction to be spent. Okay, so Bitcoin it had this language called script, and so the script it's not like a complete, like a very complete Turing. It's not like a really like a Turing complete language. So like ideally like a Turing complete language per se, but it's ideally specific. You can think of it like it was a way to ideally be able to help the network know ideally how can this particular okay, how can this particular what the correct term for the crypto is usually called unspent transaction outputs. You might hear this particular term a lot while interaction with these networks. I'm going to send this to the chat. So we might hear that term a lot, but basically it really just means the amount of, let's say like if you were sending let's say you're sending like 5 crypto to let's say to another person, and you had like 10 crypto, you had like 10 crypto, but you're sending only 5. The remaining 5 crypto you have immediately be now then spent transaction outputs. It just basically represents the amount that you have in your wallet when you are initiating the transaction. So so the script language ideally determines how the particular unspent transaction outputs can be spent by a particular transaction. And so it has its own syntax, and it's entirely its own in quotes. So I think when you be getting into Bitcoin, how basically Bitcoin really works, you'll be learning more about you will see more of this particular information and its operations. Yeah, so I think there are some questions right there. I think I can start tackling them. Unix timestamp and block number. Okay, so like let's from what we can see in the screen right there, lock time. You see the lock time right there is 969 523. Okay, so in the context of Bitcoin, we said that if the lock time right there is past 500 million, is below it's between 0 and 500 million, basically means that all the this particular transaction right here, as you can see, is only valid once when the lock time is between 500 million or 0 and 500 million, we don't interpret it as time. We interpret it as the block height. So the block height is basically the height of a particular block. As you'll be looking at the structure of a block, we have the block height. The block height is specified. Okay. So if the block height basically reaches 969,523, then this particular transaction can now be valid within the network, and we can basically we can now propagate this particular transaction throughout the whole entire network. But if it was beyond 500 million, that means that we now interpret it as a Unix timestamp. So Unix timestamp is basically just how we interpret timestamp in Linux. So it's basically the number of seconds that have elapsed since January 1st, 1970. Okay. So ideally, if the log time there is beyond 500 million, that's when we start interpreting the time as the log time as we start interpreting the log time as an actual timestamp. Right. So can a transaction expire due to time lock? Well, it's once also expiry due to time lock. Once the process of once it's in a block, I wouldn't say expiry per se. It won't expire, but it can basically it will stay within the network till it's validated. So like once you cross the threshold of authorizing, like let's say like a transaction, the only way, basically that transaction is gone. You have to wait for it now to be confirmed within the network itself. So so ideally you can't have a transaction expiring really in a blockchain network. Okay, so I've answered the questions. Right, so I think you can now proceed to the next thing. So is there any more questions on transactions? Any questions on transactions? So please, if you have any questions, feel free to ask. So now the next thing we'll be looking at is blocks. Now all these transactions that we have, they all now for them to be added to now the blockchain network itself, they have to be added to a block. Just as the name suggests, the blockchain. The building blocks of the blockchain itself is now where we have issue of time lock and timestamp. All right. Well, I'll share the notes. I'll share the notes with you guys, and I'll also supply additional material for the team to read. So don't worry. I'll be sharing this slides with everyone. Okay. So for the block, we have three main parts. The three fundamental parts of block. We have the block header. Basically, is restricted to 80 bytes. This is on Bitcoin also. Basically, it includes fields from the block described in the basic. We'll be looking at these particular bits of the block header. So it has a lot of information about the block header that we can use that is basically used to verify a transaction. So there are things like the signature, signature. We'll be looking at something called a difficulty target, and nonce. All those things we'll be looking. If you have been keen on when you're looking at blockchain explorers, you might have seen those kind of words somewhere like a nonce, difficulty target, etc. We'll be looking at them right now. Then you have a transaction counter can be variable. Basically, just contains the number of transactions in the block, including the Coinbase transaction. So remember, the Coinbase transaction is the first transaction in the block. Then the block now basically holds all the transactions in the block itself. Right. So this is now a block header. So okay, now for the block header, these are the bits that we have in the block header. We have the version. Basically, the version denotes the block validation rules to follow. So remember, with updates to the blockchain network, you do expect the rules to basically evolve as time goes. So the version right there basically tells us that basically specifies the network like which kind of rules should be used for this particular block, right? Now, previous block header hash. Basically, this basically now it presents the hash of the hash of the previous block header. Now, when you're now appending this particular block to the blockchain itself, the last block before you add this block, basically this is the hash of that particular previous block that you had there. Where the size is 60 to 32. Then you now have the Merkle root hash. And basically represents it's a hash of the Merkle tree of all transactions included in the block. So the reason as to why they use the Merkle root for this is Merkle tree for this is because of the efficiency of using a Merkle root hash. It's great. It's really great for verification and purposes, and also for ensuring that block is basically it holds integrity. It basically holds integrity. That's the purpose of the Merkle root hash. Yeah, so but you can figure that particular hash is a very, very important aspect of a block in the blockchain. Then you have a timestamp. Ideally, it's an approximate creation time of the block in a Unix epoch time format. So more precisely, this is the time when the miner has started hashing the header. So the time from the miner's point of view. Okay. Then we have the difficulty target. So the difficulty target basically is it's a value. It's basically the value that tells the level. It's basically, think of it like a level of hardness for trying to hard a particular block to the network itself. Okay, so I think possibly you've heard things about consensus algorithms and blockchains and stuff. So before, let's say, like in the case of Bitcoin, before you add a block to the network, you'd have a situation where you'd have to do like some complex math stuff, some complex math computations for you to add a particular block to the network. And so the level of this complexity is now handled by the difficulty target right there. Okay. So this difficulty target is not a daily it's not like a fixed value. It might change as the network progresses. It's variable. Okay. Then we have the nonce. A nonce, it's basically a random number. And again, this particular number changes. And it changes depending on the block, or depending on the block, or in some networks, depending on the state of the network, depending on which network you are in. It's basically like it helps the miner to ideally know at which particular point that it helps the miner to know they solve that particular the complex computation. And basically that's ideally that's the work of the nonce. It's sort of like how can I put it? It's there in the block really just to help like meet the criteria that's set by the difficulty target. And so once that particular hash has been met, or the complex computation has been basically solved, we now have a situation now where this particular block cannot be propagated. And so when other nodes are basically now verifying this particular block as being added, the difficulty target of the nodes basically be there to also assist in verification of verifying the particular result of this particular miner's work. So it'll be again, depending on whichever network you're using, most of these information, this is like sort of like the base information for most of these networks. And in terms of how this particular complex computation is achieved depends a lot on the consensus algorithm in the network again. So we'll now be looking at into this information in depth. So most of this information you cannot even in a day. They need it's more of information you build on top. So I guess as the more interactive time, we can be able to share this information with you. even during the just normal community meetups. So yeah, that's really much on the block. This is the block header itself. So is there any question on the block header before we proceed? Any questions on the block header? So please feel free to ask questions in the chat. What is a macro tree? So a macro tree, okay, so I think I've seen some questions right here. So a macro tree is it's a data structure, okay? Yeah, ideally just a data structure. It's a type of a tree data structure. So how it's formed is, it's basically just a tree, and the reason it's because of its efficiency in building efficiency in building the hash. And so the main purpose behind the macro tree was basically it's ideally to be used for hashing purposes, because it really helps. It's very efficient when it comes to it's very efficient when it comes to verification, and yeah, very for verification purposes. It's very efficient, and that's why now they settle on using a macro tree. So it is really just a data structure, a tree data structure. What's the difference between a Coinbase transaction and a Genesis transaction? Well, a Coinbase, the term is sort of like set on stone, but it's really just like the terminology is used for the same thing. Ideally, it's meant to be the first transaction that is on that particular block. So when you look at it, it only has it's basically just the first transaction on that particular block itself. So ideally, it's basically the same thing, but in theory, it's just the same thing. But most of the time, we find that people use Coinbase transaction a lot instead of Genesis transaction. But it's basically the term people took from when they're talking about a Genesis block. The Genesis block being the first block that has been mined within the network. They ended up now just passing the information also to the transaction. So the first transaction being the Genesis transaction, still the same thing as a Coinbase transaction. Yeah, thank you for that, Summer. Does this apply to all British instructions, or is it specific to Bitcoin? This depend. Yeah, if the consensus algorithm ideally using is more of how can I put it? But this is ideally you'd find like for most, I'd like to say all, but well, I'd say like for 90% of all networks, this is basically the base structure you have for block headers. Some may end up adding more information on top of this for the block, for the purpose using the network. This sort of like you can say this is like the cream. This is like the cream structure for block header. Okay. So once you basically understand how block header looks like, putting this information to other actually right. Okay, thank you for that, Samuel. Yeah, so let's see. No other question. Now this basically is how this is the deal now how ideally they all relate to each other. So you can see on the complete left we have now the blockchain itself. Then on the right you can now see like different bits. So like you can see you can see the block where we have the block height. Then there's a block. Then you have now the actual block right there with its size, the header, the transaction count, and the transactions. And you can see on the right, you can see like an expanded form of a block header. And you can see basically how a market tree looks like. As you can see, it's really just a tree data structure. You can now see the transactions and basically how they are cramped up together. I can see with the hash, the source input, destination inputs, etc. As you can see right there, then you can also see that particular script language that we're talking about, the script sig with a particular information right there. So you can see there's unlocking script and locking script. So yeah, I'll be sharing information. I'll be sharing. I can I can be linking people to books. You can look at videos you can watch more about this. So getting into the intricacies of this can take a lot of time, but it's very fun information to learn, and be happy to share all this book, share the information right there with you guys. So yeah, so ideally, just a disclaimer, not this the script sig bit is only synonymous to it's synonymous to Bitcoin. So some other networks have, that's where now smart contracts basically come into. Basically, that's where smart contracts basically come into play. Okay. For Bitcoin, we have scripts. They have a script language. For Ethereum, we have Solidity. That's we have like Solidity. This method is really, these things really change a lot. So kindly be able to understand that this is only specific to Bitcoin, the script sig. Yeah. So seeing that question in the chat. Header is a single block. No. Header is not a single block. Like we have the header is part of the block. The header basically holds information about that particular block. Okay, so instead of let's say instead of you as you're trying to verify the information in that block, instead of you oh, you got it. Okay, perfect. So instead of you trying to verify them, basically instead of you trying to check it's sort of like a way to ideally it's sort of a way to create like a checks in between what's in the block and what you expect. So if the information is more what you have on the header, okay, great. So what is a hash function in blockchain? So as a hash function is ideally a way to it's a function really is a hash. Think of a hash as a hash function ideally is it's ideally what as we'll be looking at tomorrow, it's what we call a one-way function. And so in the idea of encryption, where you can have you can ideally encrypt it function, it's sort of, you can conceal the information, but you cannot decrypt a particular information. It's one way, like it happens only one way. So ideally, that's what a hash function does. It modifies the data in such a way that it cannot be decrypted. You cannot get actual information from its output. That's really what a hash function is. We'll be looking more into depth in that tomorrow. So yeah, so I guess if there's no more questions, I think we can take a short break. We can take a short break around 5 minutes. Just stand up. Then we can come back and proceed with the remaining bits of the slides. Yeah, so please feel free to take a break. Just go drink some water. You can even just grab a snack. You can proceed at 8:15. So also please, if you have more questions, just type them in the chat. What is the role of nodes in a blockchain network? So a node. A node is basically a computer. Okay, it's really can't hear anything. Am I audible? Hello? What about now?
Yes, you are audible. We can continue. You're audible, very audible.
Right. So what is the role of nodes in a blockchain network? A node ideally is it's a computer, or ideally it's software itself. in the network. So ideally, like the network itself is a node. Okay. So so ideally for tech is just know that a node ideally the point of ideally the point of interaction with the network itself. Okay. So it's not to communicate with Bitcoin. Your point of communication in the Bitcoin network is a Bitcoin node. It's ideally the computer running the Bitcoin software. All right. Okay, so Elvis, assuming a blockchain is a linked list, assuming the links is a kind of file format, assuming one is developing a centralized blockchain, theoretically, can you transfer it from one server, say a dev server, and redeploy it somewhere? Can you restructure your question a bit? Kind of file format. One developing a blockchain network. But I hope the class lesson is informative. Please, if you have any questions, just feel free to type on the chat. Well, I guess it can't. Ideally, this information is shared within each and every single node within the network. So, ideally, this information is shared with each node. So, every node has access to the blockchain, the entire blockchain, the entire information in that blockchain network. Okay. So that's why you find that running a blockchain, but running a node can be very expensive depending on whichever network you're using. That is RAM wise and storage wise, and also electricity wise can be very expensive. So it's not per se redeploying. It wouldn't be redeploying really. You just be extending functionality to it. But that's how I'd say possibly if you restructure your question, it could be easier to answer. But yeah. I don't know. Yeah, saying it's 8:14. I think we can proceed for the next. Pardon? Okay. Yeah, we can proceed. Consensus. So remember our system is decentralized. We have to find a way of making sure that whatever is existing within the network we have to find a way of we have to find like a level way of making sure that the network is operating as we expect. The information that is being saved within the network is basically what we are informating the integrity of the network, but ensuring it can manipulate the network itself. So a blockchain network is only as good as it's only as stable and secure as its consensus algorithm. So like the meat of ideally the whole thing is a consensus algorithm. Like it really helps connect the whole technology together and basically makes sure that the tech is running as we expect it to do. So why is the consensus algorithm such a big thing? That's because that's why the point of security of blockchain network is it's in the consensus algorithm. If the consensus algorithm is weak, that basically means the whole network is weak and attackers can take control of the whole network whenever they want to. The consensus algorithm also ensures that the network is decentralized. Okay. So if you have a situation where an attacker can take over like more than 50% of the whole, more than 50% of the network, that consensus algorithm is very weak. Okay. So that's something we don't really want to happen. Algorithms chain, and it also makes it easy to track and prevent fraudulent activity within the blockchain network. Then they also ensure efficiency in the network. So since we have a same way of coming up, like just from the name itself, coming up with a consensus on a block, it helps the nodes within the network to quickly agree on the transactions and validate and add new blocks to the blockchain in a timely manner. Okay, that's why consensus algorithm is very, very okay. Consensus algorithm is very crucial thing.
Let's go in your mall,
This is think Patricia.
oppure pagati i buoni, lo
Yeah, it's okay. Now, right here we have a list of common, or a list of the block consensus algorithms that are out there. Of course, there are more, but these are some of the common consensus algorithms we meet. So we have proof of work, which is quite popular. If you know anything about the blockchain Bitcoin network, this is ideally, you must have heard this particular terminology from somewhere. We have proof of stake. For those who've had to ideally interact with Ethereum, I think you've possibly heard this from somewhere too. Ethereum or Cardano, really. Then you have delegated proof of stake. We have leased proof of stake. We have proof of authority. We have Byzantine fault tolerance. We have practical Byzantine fault tolerance. Delegated BFT. So Byzantine fault tolerance, you see some abbreviate that as BFT. Then we have this directed acyclic graphs. Then you have proof of capacity, proof of bound, proof of identity, proof of activity, proof of elapsed time, proof of importance. So ideally what you'd actually want to know about is ideally just the first two, because the first two is what ideally those are the most popular ones out there: proof of work and proof of stake. So proof of work, as I said, main bit of proof of work was that it came about with Bitcoin. So ideally that was the first consensus algorithm that was used in the blockchain network. And ideally, it's the main aim that Satoshi had in mind was that it was meant to secure the network and also prevent double spending. Okay. So proof of work ideally involves solving a very complex math problem. Remember when you're talking about the difficulty target and the norms, this is where they basically come into play. And the goal of this is that once the math problem is solved, the other nodes within the network can basically able to verify this particular information. And so as a result of this, you realize that Bitcoin nodes end up being very expensive to run and maintain. Like they drink, it's like they drink electricity. They require so much RAM. They require such an expensive, processing unit to basically use. To the point that you have like a whole industry of processors designed just to run blockchain nodes. You find that Bitcoin, because of how Bitcoin nodes, you find that it's really grown that particular industry a lot. And yeah, and you realize that because of how proof of work is, there's a certain attack that is called a 51% attack, where an attacker basically ends up having control over 51% of the network. And once they have that particular control over the network, that basically means they can manipulate as a result, proof of work, basically how proof of work basically works. Every node ideally is involved in mining this information. So the node that ends up being able to calculate being able to calculate this complex math problem. Something that's called a hash rate. Being able ideally, it has a very high hash rate. Ideally, is able to get more of the rewards. It's able to churn out more blocks to the network. And this is also the idea behind pools, where mining pools, where every single person basically comes up. They come with their own nodes. They form like a pool so that they can able to they're able to they increase their hash rate, and they can able to gain from the rewards of mining within this network. Then we also have proof of stake. Proof of stake basically, at this point, we don't have miners. What we call them is validators. And so these validators realize they hold a certain amount of stake within the network. And because they hold this particular amount of stake within the network, they are now able to validate their transactions, and they are now also allowed to add new blocks to the chain. Okay, so you realize that not every node is involved in this, but in the transactions, just have like we just have validators who have been chosen to do this. So ideally, the validators they're also in how they are. Ideally, I think a question they'd have is if we end up choosing validators who can now, like, the work is to validate the transactions in the blockchain network. How do you prevent them from ideally committing fraud within the network? So, how this is controlled is that in the proof of stake design is that there's incentivizing bit where, of course, since you validate, you get a bit of something from the work you've done. But also if you end up doing something that's contrary to the rules of the network, they may end up losing the stake within the network for that. So you end up finding that it's really hard for the validators to ideally end up committing fraud within the network or try to attack the network itself. So proof of work versus proof of stake. So proof of stake ideally promotes decentralization. Okay. So remember how I talked about the more computing power you have in the Bitcoin as a Bitcoin node basically means that you have a very high hash rate. And the higher your hash rate basically means that you can basically churn out more blocks. And if you end up having a mining pool that has a insanely high hash rate, and you end up, let's say, like churning out, like, you can even just say 10% of the nodes, and ideally that now becomes a case of possible centralization. Okay, but proof of stake basically basically ends up assisting to prevent that from happening. All right. Okay, proof of stake can lead to proof of stake, of course, not entirely perfect. It can end up leading to a get richer situation. So what happens if a validator has quite a very large stake within the network? That basically means that every single time your node basically is being chosen to basically act as a to validate the transactions and add blocks to the network itself. So this is prevented by you might find that in some implementations of proof of stake, there's a random selection of validators, and you might also end up limiting the amount of stake a particular validator can hold. Okay, that's much on that point. Then proof of stake is also less energy intensive. So as I talked about proof of work, where really maintaining a Bitcoin node is quite expensive. It's quite heavy. Okay. Maintaining a Bitcoin node is quite intense because of the amount of work it has to do. So proof of stake is much simpler to handle. It's less energy intensive, and as a result, it ends up being very environmental friendly and and cheaper to basically run. So I'm seeing there's a question here from AGK about proof of work. So let me give an example. Let's say this is this is the complex challenge that we have to compute for computers. Then let's say like okay, let's say that is a challenge that we have to let's say that is a challenge that we have to do. So ideally for proof of work, we'd have to have every single person in this meeting right here, yeah? Every single person try to find the answer to that particular question right there. Okay. So assuming that this is quite a very complex thing to calculate, you see that we now sort of like there's this particular proof of like I've done a bit of work. So this is a block that I'm churning out. And the idea behind proof of work is that we all have to calculate this particular computation, and the first person to basically get the answer propagates the answer to the whole network. They propagates the answer to the network itself. And yeah, and you realize that it's all like the blocks. I think another thing I have to mention is that the blocks are not added immediately into the network. They are confirmed after also a specific amount of time. So if you transact within a blockchain network, you might have, let's say like in Ethereum, you might have realized that your transactions were only accepted after they're only confirmed after a specific amount of time, let's say like around 4 minutes. So that basically depends. It also depends on the network itself. But back to proof of work, and so the idea behind proof of work is we all make the complex computation, and the first person to basically come up with the answer is the one who now basically adds the block to basically is the one who adds the block to the network, and is basically the one who ideally gets the incentives. That's the idea behind proof of work. Okay, that's ideally just proof of work. There's a complex computation to be made. We all have to calculate it. Once we get the answer, the one who gets the answer the one who gets the answer the fastest basically gets gets the incentives from mining that information. That's basically the idea behind mining. For you to basically add add a block to the network, you have to do some work for it. Okay. Hope I've answered your question. All right. Go to the next slide. So not much on consensus algorithms. So when you get the slides, please take time to go through these other ones. So depending on whichever network you're working on, you might end up having a different consensus algorithm you have to understand. So please always make sure that you are very much acquainted with the consensus algorithm with the network you're working on. So virtual machines. Remember how in Bitcoin I said we had like a script language to help in understanding the kind of ideally just to help us in understanding how the crypto that is in that particular transaction has to be spent. You might realize that that script right there is not entirely like it's very limited in its capabilities. For those who are nerds in terms of how programming languages are designed, the script is not Turing complete. It has its limitations. So as a result, we now have the introduction of virtual machines. So ideally, the virtual machine it allows you to run, as you can see, Turing complete code in the blockchain itself, and that's basically where the idea of smart contracts came from. Okay. So a good example of virtual machine is the Ethereum virtual machine. And so because of the EVM, you can now be able to run smart contracts on the EVM, and you'll be able to write extremely complex smart contracts that you can never even write them in the Bitcoin network. Okay. That's basically the idea behind the virtual machine. So the intricacies of virtual machines won't be able to look at them, but whenever you can, please be free to research, and I'll be able to answer any questions you might have on virtual machines. So we can look at smart contracts. Yeah, smart contracts ideally, as we said, they are basically programs that can run on top of the blockchain. And ideally, they just encapsulate business logic that are executed whenever certain conditions are met. So that's why you find them, they're very good at handling escrow payments. Yeah, can be very good in things like supply, like handling quite very difficult, like say very complex logic. You can be able to write them on the blockchain network because of smart contracts, ideally. And so, yeah, I think, well, before we proceed to the next slide, I think you can just type in the chat. What do you think, just from the information you've learned about the blockchain itself? What do you think are the different use cases for blockchain network? So like, with all this information that we've just seen about a blockchain network, why do you think it's such a big deal in the world? So like, if you were given access to basically build anything in the blockchain, what exactly would you build? So yeah, it's a question. Yeah, blockchain and cryptography go hand in hand. So as you'll be going deeper in blockchain development, Web3 development, you'd basically also grow in terms of your cybersecurity skills. Would definitely grow, and that also includes your knowledge on cryptography. Yeah. So it's not very hard. It just needs a bit more reading, really. Yeah. So use cases of blockchain network. So what do you think you can do with the blockchain? I'll go first. Okay, basically finance. Everything finance can be done on the blockchain. What else do you think can be done on the blockchain? Record keeping. Okay, good. Thank you, Brighton. Voting is good. Can do voting. Yeah, polls. Very good. All right, good. Thank you, Mateo. Yeah, so yeah, Stacy, smart contracts. What are the smart contracts do? Right, I'm seeing NFTs, security information, air ticketing platform, very interesting ideas out here. Security. So what do you mean by security? It's a very hard name, man. Decaristian. Energy trading, interesting. Yes. Building wallets. Building wallets for what, NASA? Come on, man. College degrees. Yeah, that's actually a very good use case. It's logistical tracking. Yes, yes. Perfect. Transparent election voting. That's good. Yeah, Stacy, smart contracts. What exactly is smart contracts? Manage healthcare data. Good, good. There's actually a very good startup that does that in Kenya. There's actually blockchain networks that are very good energy distribution. The blockchain networks are actually designed specifically for IoT devices, secure online transactions, good. So yeah, even for IoT, you can use IoT for that. There's also, I don't know whether you've heard of decentralized operating system. There is actually one out there. I think I'm just forgetting the name, but there is one out there. Yeah, fake products identification systems, good. Yeah, that looks like a supply chain thing. Storing irreversible information, good. Very, very good. Asset storage, very good. Security and keeping records are perfect. You guys are on track. They are very much on track to become pioneers in this website, in this industry. Master degree in blockchain and smart contracts. Well, yeah. Healthcare, yeah, that's good. Yeah, thank you very much, Stacy. It's very accurate. Yeah, I think so. I've forgotten. But once I get it, I'll share the group. Real estate tracking of location. Thank you so much for participating. So technically, yes, that's basically what you can do. You're not very limited to what you can do with the blockchain. The possibilities are endless. So you're only limited with you're really only limited with with your imagination. Line registration, good. Stop patient data, perfect. So, well, I think the last thing you'll be looking at is types of blockchains. Yeah, in logistics. Thank you very much, Abraham and Ejiko and Ejike and Warren. Thank you so much for your contributions. So types of blockchains, we have those four. The main four are those. So we have the public blockchains, which ideally we all know, guys like Bitcoin, Ethereum, Cardano, Polygon, etc. Basically, a public blockchain, like anyone can access the network, they can use it, and we can leave, and we don't really have to know. Basically, they really are. We just have to transact with them, and we move on with our lives. That's basically public blockchains. Private blockchains, on the other hand, there's a limit to who can access the networks, and there's also a limit to the rights you have in that network. A good example is a triple or hyperledger fabric. Okay, so use cases for private blockchains could be things like supply chain. So let's say that the country needs to govern basically how they need to understand how, like a packet of maize. Basically, let's say like if you buy like a whole band of maize, the government buys a whole band of maize, or the company buys a whole band of maize. And the government needs to understand basically the whole process of how this maize was moved from the cob to, let's say, to flour, okay, to maize flour. So this could be basically managed by a private blockchain that is specialized for handling supply chain activities. You can have one for internal voting, can have one for asset ownership, okay? So you might find that the Hyperledger Fabric is actually it's a suite of it's the IBM team created like a suite of networks that can handle this kind of stuff very well. So you can find one that's really designed very well to handle things like identity. Yeah, there should be one for supply chains and stuff. Yeah. So the tokenization real estate, tokenization is very powerful. Now, we now go to consortium of federated blockchains. So basically you can think of them as not hybrid per se. I think that's an error in the notes, but not hybrid per se, but they are ideally semi-decentralized. Okay, they're semi-public, semi-private. Like you might find that a company wants to the people in managing the network, they want to control the amount of publicity, the amount of things that can be made public to the entire world. Okay, so as they say, like a good example would be like a bank. Okay, a bank wouldn't want the whole entire information to be out in the public. So what they do is they do an application like a consortium blockchain. Okay, where they can now be able to publicize things that they need to be public, but they can have their own internal things being still. They can have them within the network itself, but doesn't mean that you basically immediately being able to wait for info. Not I think you have a problem in the network if you can't hear me. I really like you want sort of like you have a degree of information being publicized to the public. So kindly just so ideally that's really the idea behind consortium blockchains. Yeah, so it's basically semi-decentralized. And the interesting thing about consortium blockchains is that because of how they're designed, what is the uniqueness of blockchain? Can you just expand on that question a bit? Because of how they're designed, you may realize that some of the consortium blockchains are actually very scalable, and they have a high transaction throughput than most public blockchains. Okay, so yeah, so ideally some things are kept public, whereas others are kept private. Then the last ones we have is hybrid blockchains. So ideally they try to combine best of both worlds. Okay, where you can have flexibility in terms of permissions and depending also on the use cases you have. A good example you have is Dragon Chain. I think there's another one called Komodo. that's designed on that's sort of like built on the block on Bitcoin itself. Yeah, so you may realize that there's a very big, very wide world of very wide world out there on when it comes to Web3 development. So always keep your eyes open. So much to learn out here. Yes, then I think honorable mentions, you can have permission block public blockchains. So I'll be answering your questions in a few. We can have permission public blockchains. So basically there's a public networks. The web participants they need permission to join, perform certain actions. Okay. So a good example would be, could be, let's say like you want to control like voting and stuff, you can do that. Okay. You can have a permission blockchain for that. Then you also come and you also meet the concept of something called sidechains. So a sidechain basically is a separate blockchain connected to a primary blockchain network. Okay. So a good example would be basically like you'll be beating sidechains a lot when you're doing your Web3 development. So the idea behind sidechains is that they help they are very good in terms of scalability, interoperability, also for experimentation. They're very, very good for that. Okay. So yeah, that's really it. So I think our first assignment we can have basically that. So once you form the groups, we'd like to spend the first 30 minutes tomorrow on group presentations. So please, I'm expecting a few of the groups to present something on overview of different blockchain networks. So what I mean is at least in what you be talking to us about, be it that you can explain to us, let's say if you be talking about Ethereum, at least tell us what is the consensus algorithm, give us a slight history of it. Tell us of anything interesting that happened within the network within within its development. If it tell us about if it has any virtual machine, like any sort of virtual machine it uses, if it has like does it use a smart contract language, does it have like its own script, etc., etc., etc. So so I think that's really why we're trying to finish a bit earlier today, so that you can be able to form your groups and you can be able to start working on the assignments. Then I think for personal reading, you can look more into transaction outputs and inputs. You can also look into the UTXO models for people, especially for guys who will be moving to will be very interested in working on Cardano. Understanding the UTXO model it will help you very much in understanding how Cardano basically works. But yeah, so that's a first group assignment for today. So please make sure that you can form the groups. I think in terms of how the groups will be formed, I think we can have like a very short breakout session in a few. Hopefully they be as random as possible. I don't know whether that's possible, Europe. If not, I think it can be coordinated from the WhatsApp group if that's not possible. But I think I can answer the questions quickly before we do that. So I think Edna's first question was a group of 5, yes, perfect. Edna's first question was on the what makes a block unique in blockchain technology. Well, we can see a block can be unique in terms of the timestamp. Of course, since you don't expect the same, you can really have it. You can really have, it's quite hard, almost impossible to have a block or two blocks within the same timestamp having the same information within it. Okay, basically that what makes a block very unique. So like the nonce is it's randomized. The difficulty target might not be the same. The timestamp might be the same, but the hash might be different because the transactions that are basically being held by the block. Okay. Yeah, the session is being shared. It will be shared with you. It's being recorded. Will you kindly share examples of a private blockchain provider? yeah, we have yeah, as I said, we have REPL. You can also look into Hyperledger for that. Okay, younger can have that specific programming. Any tool that you're comfortable with is okay. If you're comfortable with Visual Studio Code, well and good. If you can use any text editor is okay, really. Is there a market available after learning to use a skill? Yes, there is a market available. A lot of VCs are coming to Nairobi to a lot of VCs actually coming to Africa to find startups to fund for this kind of work. So if you have a good idea, if you have a very good idea on solving issues that are there in the continent, in your country, in the continent at large, then the market is very much available for you. So I think I saw another question about programming language. Oh, Baraka, yes. Specific programming languages you should not work with the blockchain. It depends on the blockchain network you're using. Some use Rust like Solana. Some use Haskell like Cardano. Some can use Python like Algorand. Some have their own, like Ethereum has Solidity. JavaScript is sort of like universal because yeah, you have to find a way of making sure that your users can really interact with the smart contract. So yeah, I'd say JavaScript is a good point to start with. So what kind of coding skills do you need to have become a blockchain developer? Well, yeah, as I said, JavaScript is very much across it's a cross-cutting concern really. But really you should also be able to understand cryptography a bit. So we'll be looking into that tomorrow. Ideally being able to understand a lot of the terminologies will be meeting out there when you're learning on how to write your smart contracts and how to interact with the blockchain network itself. So yeah, really much it's more so just being able to understand the smart contract language you're working with. But most of these skills can be learned, so don't be really worried on the coding skills. Okay. Yes, thank you for that, David. So yeah, I think that's it for today. Well, I don't know whether it's possible to. Is there a place for cybersecurity students and blockchain? Very much there is. There is actually a very big. There's a very big need for cybersecurity experts in the blockchain. Very big, yeah. So keep the questions coming. Yeah. So how long does it take to learn? Well, it doesn't take really long. It doesn't take really long. Okay, so don't be worried. It's you just need to read. You just need to read a lot. Okay. Ledgers and smart contracts. So a ledger is a way of saving information. A smart contract is an executable piece of code. So think of a ledger like the information that is being stored, and the contract basically is you can think of a way of updating the ledger itself. Okay, I think we can going to have randomized breakout rooms of 5 people. Okay, so perfect. So now what we'll do is you can choose a room to join. Yeah, kindly just choose a room to join and meet up with your group mates. Okay. Oops. Uh, okay. So you'll be added to your groups in a few.